So in the last couple of lectures, we looked at a case where we could solve the field equations exactly, find a solution, and that was the case of the static isotropic metric where Schwarzschild found this solution, right? And the solution depended on this function a of r, right, which was equal to b to the minus 1 of r, and which was 1 over 1 minus 2 mg divided by r, right? And so what we're going to discuss today instead is an approximation by which we write the metric as some background, which in fact will be flat, plus a perturbation, and then work out what the equations are for that perturbation. The reason for that, of course, is that there's not many cases where you can find an exact solution to the field equations. So you need to find some sort of approximation, and a reasonable approximation to do is one where you assume that the field somehow is weak, right? And in fact, we have used this idea that the field could be treated as weak already when we discussed, for example, orbits, right? Because in the end, when we calculated the precessional perihelion Mercury, we actually took this function and expanded it out, right? So this is equal to plus 1 plus 2 mg divided by r, right, plus dot, 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 right? And so when you do this expansion, in the cases that we looked at, you get the correct answer, right? Because the correction then from higher order terms is very small, right? So we are going in this lecture to develop this weak field expansion systematically, right? Which means that we are now going to write the metric g mu nu of x as eta mu nu, right? Plus some perturbation, which is h mu nu of x, which is supposed to be small in some sense. Right, supposed to be small. Now, when we expand the metric in this way, of course, we could expand about some background metric, which is not necessarily flat, right? So this one's flat, is the flat metric. So it's a metric that is just ones and minus one along the diagonal. But it is certainly possible also to consider a metric which has some curvature as a background, right? So you could do that as well. And then if you do that, then this eta mu nu would be some sort of background metric, which we would call g tilde mu nu. And that, of course, would depend on x, right? And so you can do the same expansion, right? But we want to keep things simple. And as a result, we are going to just expand around the flat metric. Because if we do so, then it is easy, fairly easy to work out what comes out of it. Right? But that, of course, is not the most general case. Right? So then the other issue is, of course, what do we mean when we say that the field is weak, right? That the h is small, right? Well, we have seen already in this case, right, we have an example of it for the Schwarzschild solution. We can look at an explicit form of the metric. And in that case, we can make a statement of what it means to be weak, right? So here, weak field means essentially that mg divided by c squared r is much smaller than 1, right? This is small, right? And so that means that we have, of course, another regime, which is the regime of strong gravity, right? The regime of strong gravity is one where this condition is not met, right? Is one where this condition is not met. So strong gravity is a regime in which mg divided by c squared r is of order 1, right? Is of order 1. And that is clearly the regime that cannot be reached by using the kind of expansion that we are going to be doing in a little bit. And well, you might think that such a regime does not occur very frequently, but in fact, it is easy to see that there are a number of astrophysical situations where, in fact, we have precisely this kind of relationship, and in which case, of course, the weak field expansion does not work, is not particularly useful, right? So the regime of strong gravity is a regime where the mass is large, right? So whenever you have a large mass, you have to be concerned about gravity getting strong. And of course, at the same time, the relevant length scale, right, the r being small, right? So whenever you have a massive object that has a relatively small size, a small dimension, then you will be in a regime of strong gravity, and therefore the weak field expansion is most likely not particularly useful. Nevertheless, it could be a starting point to try to understand what is going on, right, but it's not necessarily reliable, right? The other thing perhaps that is useful to point out at this point is that if you look at the weak field expansion, you're expanding in this small field, and the small field in this case, of course, is this 2mg over r correction, right? And so we have, in the case of the Schwarzschild solution, we have, in fact, a case where this infinite series has been resummed. So the weak field limit would just give the first term, but there are infinitely many terms, right? Because the actual answer is its geometric series is 1 minus that, right? And so just by looking at the first term, you would not be able to tell that actually this function is singular, right? Because of this singularity, right? So there is a big difference between just having the first term and having the whole series summed up. And so in the weak field limit, you're losing some of the important aspects of the theory, but nevertheless, you at the same time are able to gain, as we shall see, a better physical understanding of what happens in certain situations. For example, when you meet a gravitational wave, right? Now, one last point which I want to bring up is that in the quantum theory, so in quantum mechanics, right, then of course you are, in Feynman's path integral approach, you're summing over all paths. And in this case, it means summing over all h mu nus, right? Because you're going to do a functional integral over the gravitational field. And when you do a gravitational a functional integral, then basically the dh mu nu is going to be integrated between minus infinity and plus infinity, right? Because that is one of the characteristics of the quantum theory, that you have fluctuations, and that those fluctuations have to be integrated over. And so basically, in the case of a quantum theory, you're never in the weak field limit. In the quantum treatment, you cannot restrict yourself to the weak field limit in general, because the fluctuations will be there, and there is no way to constrain those fluctuations to be small, right? This is something that we do not have in the classical treatment, because in the classical treatment, we have a way of controlling those fluctuations by looking at specific physical situations where the fluctuation is small because of, for example, an argument of this type, right? But quantum mechanically, that does not go through, and so in the quantum mechanics case, we cannot do this kind of approximations very easily without running into very serious trouble. So let's now look back at the field equations. So we start out with the field equations, which is r mu nu minus a half g mu nu times r is equal to minus 8 pi g t mu nu, right? And for the time being, we will take the cosmological constant to be 0. It will simplify things a little bit, and we can always go back and add that at a later stage. So we want to develop everything in a power series in the h, right? So the leading term is the flat metric. And of course, when you take any derivative of the flat metric, you're going to get 0, right? So if we look at the Riemann tensor is something like a derivative of affine connection minus some other derivatives of the affine connection plus gamma gamma minus gamma gamma terms, right? And the gamma in turn, of course, is, right? I'm not talking about the scalar curvature here. I'm talking about the full Riemann tensor, right, with all its indices. And the affine connection itself is 1/2 times g to the minus 1 times dg plus dg minus dg, right, again with some suitable combination of indices. And so we need to expand all these things out by setting, right, by setting essentially g is equal to, well, the flat metric, right, which is like an identity, plus the h, right? And so, well, the derivatives of flat metric, of course, are 0, so the affine connection starts out as h, derivative of h, right? And so then we have to sit down and do all these things and work out what the weak field limit is. Nevertheless, these terms are of order h squared for the simple reason that they contain gamma twice, right? They contain the product of gamma with itself, which means that we can just limit ourselves to the linear part of, say, the Ricci tensor. So we only need the linear part of the Ricci tensor for what we'll be talking about. So linear part of Ricci, right? And so that is going to be r mu nu is equal to d by dx nu. There's quite a bit of algebra that's going to come up today. It's kind of unavoidable. And we'll just have to go through this. And then when we get some answer, we can just stare at it for a little bit. So derivative with respect to x nu of gamma lambda lambda mu, right, minus the derivative with respect to x nu, gamma lambda mu nu, and then plus terms which are order h squared, right? So this is the part that we need to work out. And the gamma lambda itself, gamma lambda mu nu, as advertised, contains a part which is linear in h, which is of the following form, the 1/2 in front. The g to the minus 1 here, we can expand that just to lowest order will give us the eta only, because the next term is going to be of order h, which multiplied by these terms, which are also of order h, is going to give us terms of order h squared, which we neglect. So we just need the flat metric in front. So we need just the eta lambda rho, right? And then times the derivative with respect to x mu of h rho nu plus the derivative with respect to x nu of h rho mu. And then the remaining term, which is the derivative with respect to x rho of h mu nu. Right, close parenthesis. Right, and so that goes in there, and it goes in there. Right, and that is what we need. So plus terms which are order h squared. Right, plus terms which are order h squared. Right. So now, because the background metric is the flat metric, we can just raise and lower indices using the eta. So to this order, we can, for example, when we want to raise one index, so we want to have this index upstairs, then we can just use the eta. So we can use eta lambda rho times h rho nu and do it in this way. Right? So all we need at this stage to bring indices up and down is the eta, which means that now there is really not much of a difference between index upstairs and index downstairs, because the eta is just a constant matrix, right? The minus 1, 1, 1, 1. Right? Very good. So now we put everything together, and we get an expression for the Ricci tensor, right? Which is basically all we need as far as the field equations are concerned, right? We don't care about the full expression for Riemann. And so the Ricci tensor is going to be 1/2 times, we get 4 terms. So the first one is just a box of h mu nu, right? So the box in our case is, because of choice of metric, is minus 1 over c squared d by dt squared plus the gradient squared. Okay, so that's our box, right? So box of h mu nu, the Lambertian of h mu nu, minus the second derivative of dx lambda by dx mu of h lambda nu minus the second derivative with respect to x lambda and x nu of h lambda mu. Right. So plus the second derivative with respect to x mu and x nu of h lambda lambda. Right. We will refer to this last entry as basically the trace, because you see that you take the fluctuation in the metric and then you set just the two indices equal. So that's the trace part, right? And sorry, this is a minus sign, by the way. Sorry, minus, minus, plus. And so let me just check the indices again, mu and nu and mu, lambda, 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 lambda. So plus terms, which are order h squared, right? And this is equal to the source term, right? The source term. Now remember, you can write the field equations as r mu nu minus a half g mu nu r, or you can bring the trace part, the r part, you can bring it over on the other side and write the source term as t mu nu minus a half g mu nu times the trace of t, which is what we're going to do here. So we're going to write this as minus 16 pi g times Newton's constant times s mu nu, right? This s mu nu. So the s mu nu is the same as the t mu nu, where you subtract the trace part. So minus 1/2 eta mu nu to this order. We just need the flat metric, and then times the trace, which is t lambda lambda, right? And in some books, this is denoted by t bar mu nu, t bar mu nu. For example, Feynman uses the t bar instead of introducing a new tensor S, okay? So when you do this kind of procedure, that's called the trace reversed version of the original tensor. So by this trace reversing, we're actually, what we are avoiding is having to add also the r term part, because we just move that over to the source term, right? Now, the equations as they stand are fairly complicated at this stage, right? We can, if you want, delete this part, right? And say that that the weak field limit of Einstein's equations reduces to this, right? It would have been nice if we just had a single term on the left-hand side, but we don't, right? So we definitely have some sort of a source term on the right-hand side, but on this side we have 4 terms. The first one, of course, we recognize as just a wave equation contribution, right? The standard de Labertian that appears in the wave equation. But these other things are a little bit more of a mess and a complication. And so what to do about those? By the way, I should add that it is possible to streamline this notation a little bit, that we don't have to actually write it all in this form by writing all explicitly all the derivatives, because, well, we're going to continue using this notation, but nevertheless, one can write things in a slightly more compact way. So, for example, this term here, as an example, we can write that as d lambda d mu h lambda nu. We can write it by just having the derivative written in this form instead of writing explicitly the d by dx symbol. So nevertheless, we'll kind of stick to this notation for a little bit. So the S, right, if you look at, we know that the t mu nu is conserved. So we do know that d by dx mu, say, of t mu nu is equal to 0, right? And so that we can work out what the divergence is of the S mu nu, because the divergence of the S mu nu is the divergence of t mu nu, which is of course 0, and then the other divergence of the other piece. So as a result, we have that the divergence of S mu nu, right, is not equal to 0, but is equal to 1/2 of the dx nu of S lambda nu. Right, so we can't assume that it's 0. Nevertheless, it does have a simple form, so that's one thing to keep in mind. The second thing to keep in mind is that the Bianchi identities are still satisfied in their weak field form, right? So in their weak field form, we have that when we take the ordinary derivative, with respect to x mu of r mu nu, right? This is equal, in our case, to just 1/2 times d by dx nu of r lambda nu. Sorry, r lambda lambda. Right? We have an index mu on both sides like this, and then of course plus terms, which are order h, right? So high order corrections. Actually, it turns out to be order h squared. So, what to do next? Well, the third item, of course, is what happens to general coordinate invariance. So what happens to general coordinate invariance in this formulation where we no longer have the original metric, but we just have the h mu nu, right? So there's going to be some property of the h mu nu that is a remnant of the general coordinate invariance of the original theory, right? So that means that we are going to write out what general coordinate invariance means when we have a metric that is just a deformation of the flat metric. Right? So let's do that. Right? So general coordinate invariance means, well, in the original form, of course, it means that g prime mu nu transforms in a way that involves some derivatives, right? So dx prime mu by dx and dx prime nu by dx, and say with lambda and rho, and this is then g lambda and rho, right? It transforms according to the product of these things, right? Except that in our case, this quantity here is eta mu nu. Remember, this is the inverse metric. It has the indices upstairs. So as a result, this is eta mu nu minus h prime mu nu, right? And now we're going to write the coordinate transformation as an infinitesimal transformation. So infinitesimal form. Normally, of course, it is just x prime, sorry, I should say x mu goes into x prime mu, right? But here we're going to write the infinitesimal form, which is that x mu goes into x prime mu, which is going to be equal to the original x mu plus, right? Everything is a small change, so it's a small modification of the flat metric as far as the g mu nu is concerned, and it's a small deformation of the coordinates as far as the x is concerned. So we're going to write this as plus some epsilon mu of x, where this is again small, right? This is a small coordinate change, right? So we think of an initial coordinate system which looks like that, right? And now we do a slight deformation of that. So a slight deformation of our coordinates. Well, that slight deformation, of course, depends on the point you're at. So it's done everywhere, but it's small, right? So, well, that means that now we can insert the derivative of x prime with respect to x is going to give us this epsilon, right, plus a term, which is just a Kronecker delta, right? So this becomes the Kronecker delta part, delta mu lambda, right, plus this epsilon function. And because it depends on x, this is not 0. So we get the epsilon mu by dx lambda, right? And that goes in there, right? And, well, same thing for this other piece, right? That becomes delta mu nu rho, right? The indices are different, but otherwise it's the same form. Delta nu rho plus the derivative of epsilon nu with respect to x rho, right? And, well, finally, for this part, for this metric out here, well, that's again the metric is going to be our g mu nu minus h mu nu, right? So as a result, we have, now the leading term, of course, cancels out between this thing and all the ones that we have here. So the leading term cancels out, and so what we have is just an h prime mu nu, which is related by, so it's the same as h mu nu, and then plus the terms which are of order epsilon. And the terms of order epsilon in this case are, because of the appearance of the minus sign here, are negative. So we get minus d epsilon mu. And so with one derivative, right, the derivative with respect to x lambda, right, that's that term right there. Derivative with respect to x lambda of eta nu lambda, right, or lambda nu. That's right, is lambda nu. Right, and then the second term, which is the other cross term involving that derivative there, so plus the derivative with respect to epsilon nu of dx lambda, or dx rho, we can call it any way we want because it's summed over, so times eta rho mu. Okay. Well, this looks still slightly messy, but the reason why it looks messy is because we still have the etas in there, right? So let's just lower these indices. If you lower the indices, then you get rid of the eta, right? So it is just simply h prime mu nu is equal to h mu nu minus d epsilon mu by dx nu minus d epsilon nu by dx mu. Right, and plus terms which are of order h squared, but which we don't care about. Right, so that's the transformation property. Again, let me check the indices: mu nu, mu, nu, nu, mu. So that's the transformation properties of the metric in the weak field limit. Right, so in the weak field limit, this is how it transforms. So you can see that in fact it is not too complicated to remember. And as soon as you stare at this result, of course, it looks familiar. Right? It looks familiar because it is similar to what we have in electromagnetism, right? Because in electromagnetism, we have a prime mu is equal to a mu, right, plus a derivative, right, d mu of some function chi, right? And that function chi is just a gauge transformation function, right? In electromagnetism. So there is a gauge transformation in electromagnetism, but in electromagnetism, of course, it is just a scalar function, right? The way the field, which is a 4-vector, transforms is to the derivative of that function, and that allows us to make, of course, a 4-vector out of just a simple scalar. This is very similar, right? This is very similar. But the substantial difference is that the field starts out with more indices. Right? There's 10 different components of the h mu nu. There's only 4 electromagnetic potentials. And the gauge function, right, that enters into the transformation law, instead of being a scalar like in electromagnetism, is now a 4-vector. Right? So the gauge function is a 4-vector. There's 4 of them instead of just 1. And nevertheless, this is the gauge invariance of the weak field limit of Einstein's theory. So this is the gauge invariance, right? This is the gauge invariance that we have here, and the reason why we call it by that name is, of course, because it's precisely the analog of what we have in electromagnetism. So that, of course, is very interesting. It also shows that this gauge invariance that you have in Einstein's theory is nothing but the original general coordinate invariance written out in the weak field limit, right? So general coordinate invariance and gauge invariance, well, we cannot say that they're the same, but they're closely related. We are talking about basically the same thing, right? So the original general coordinate invariance that applies to the full theory, right, with the full field equation, which states that different observers will describe physics by the same set of equations. When you look at what it becomes in the weak field limit, it becomes some sort of gauge invariance like the one of electromagnetism, right? And the parameters that appear in that gauge transformation are nothing but the shifts in the coordinates, right? So the shifts in the coordinates are these gauge parameters, right? These 4 gauge functions which we denote by epsilon mu. And that is, of course, is a profound insight. It's a profound insight because, again, of course, one more time, it tells us that there is a deep analogy, there is a deep similarity between electromagnetism and Einstein's theory, that you can almost not quite, but almost map one-to-one between what happens in one theory and what happens in the other theory. And certainly the appearance of this fundamental invariance is crucial in doing this sort of mapping, right? So that is very interesting, and it is something that we have to keep in mind, right? It ends up being just at the bottom of the blackboard in a relatively small box, but this box is just as important as this box, right? Because the invariance of the theory under these gauge transformations allows us to do what? Well, it allows us to do the same kind of games we do in electromagnetism, right? Because in electromagnetism, of course, we like to work with equations that are as simple as possible. And when we try to make the equations as simple as possible, we end up imposing a condition, which is usually referred to as a gauge condition, right? So you impose a gauge condition, which could be some sort of Lorentz gauge or Coulomb gauge, right? And so in our case, we're going to do the same. Right? We're going to do the same, and I don't want to erase that one because I certainly don't want to rewrite it. And so I'm going to leave that on the blackboard, and we'll leave this thing also on the blackboard, right? And so right, so in electromagnetism, right, we have A prime mu is equal to A mu plus, say, d mu chi, right? And this invariance is usually reduced by requiring, for example, that divergence of A is equal to 0 and phi is equal to 0. Or we can impose something like this Landau gauge that A mu is equal to 0. So we have a number of different choices on what kind of gauge condition we want to impose in electromagnetism. And as I said, we're going to play the same game here, right? And so the gauge condition we're going to impose is precisely this harmonic gauge condition, right? So harmonic gauge. Right, which was this coordinate condition that we introduced a couple of lectures ago, right? And that was that g mu nu, gamma lambda mu nu is equal to 0, right? Now, of course, this is a gauge condition, and the reason why you recognize this as being a gauge condition is the fact that the gamma is, in fact, not a tensor, right? The gamma is not a tensor, so we restrict something that is intrinsically non-invariant to have a certain condition satisfied, right? And so now we need to work out what this is in our limit again. Again, we use the fact that gamma is equal to 1/2 times, remember this, dg minus dg plus dg, right? So we plug that in, and we also have the g mu nu is equal to eta mu nu plus h mu nu, right? So this is going to give us a constraint on what? Well, clearly on derivatives of the metric, but more specifically in this case on derivative of the h's, right? And so to linear order, that is the leading term, is that we just get that d by dx mu. So in principle, we have 3 terms, but 2 of them are, sorry, this should be a plus, of course, and this should be a minus. So the first 2 terms give the same contribution, and then the remaining third one is something different. So we get d by dx mu, h mu nu, minus 1/2, so that's the last term, is d by dx nu times h lambda lambda is equal to 0. Right? So plus terms which are order h squared. Right? So the harmonic gauge condition does not tell us, right? It is not of the type d mu h mu nu is equal to 0. It is not of that form. It is of the form that some divergence is equal to a divergence of the trace, right? And there is this factor of 1/2. And so you wonder, well, why did anybody come up with something like this, and why not choose a different type of gauge condition? Well, there is a very simple reason for that, and that is that this condition makes precisely these 3 terms go to 0. leave that to you as an exercise to show that. And in fact, again, we see the trace part as being the last term, right? So this is a trace part like what we have here. And the 1/2 is just right to accommodate for the fact that here there is only one trace term, but there are two terms that do not involve the trace that have the h mu nu. And so the relative sign is what appears there and is what leads to that cancellation. And so that, of course, is the reason why this harmonic gauge condition is so popular, right? The harmonic gauge condition is so popular because as a result of this, we just have that box h mu nu. So all of this and all of that is 0 in the harmonic gauge, right? And so what we're just left over is minus 16 pi g times s mu nu. So minus 16 pi g times s mu nu. Right? Minus 16 pi g times s mu nu, right? So we can, in fact, now write something that looks a lot like electromagnetism, right? Let me remind you that in electromagnetism, you have that box, a mu for a suitable gauge is equal to minus j mu, right? You can write it in this form. So here we have the same thing, that we have been able to get rid of various other annoying terms that involve d mu a nu, and just write it in this simple form, right? And so that, of course, has an immediate solution that h mu nu of x, right, is equal to 1 over box times 16 pi g times s mu nu with a minus sign in front, right? So the h mu nu can be written in terms of the inverse of the D'Alembertian. Now, the inverse of the D'Alembertian is usually calculated, well, that, of course, you can look up in Jackson. That is not something that we need to go through here again, because this equation, as far as it stands, is exactly the same that you have in electromagnetism, except that this field has two indices instead of one, but that really doesn't make a whole lot of difference. The important thing is that this depends on x, and that this depends on x, and that you have to invert it. And when you do the inversion of the D'Alembertian, right, you get then, of course, retarded and advanced potentials, right, here, as well as in electromagnetism. And the one that is, of course, relevant for our case is the retarded one. Right, so we need the one that obeys causality, and so that is done by suitably applying boundary conditions. So in this case, we have the same thing, right? So we have that h mu nu, and so you can write it in terms of, so this is a retarded solution, right? The retarded solution is that h mu nu of x and t. So we use the fact that if you want the Fourier transform of 1 over r is 4 pi over k squared, right? You can do that by Fourier transforms very easily, and that gets rid of the pi here when you invert that. And so this is just 4 times g times the integral in d3x prime of the source term, right, the s mu nu, right, of x, evaluated at t minus x prime, right? And then divided by x minus x prime. And so that provides the general solution to this problem, right? X prime here. So as in Jackson, right, with h mu nu of x getting replaced, in Jackson by a mu of x or vector potential, right, with that correspondence, right? Again, the only thing that really matters is that these are functions of x. It doesn't matter how many indices they have. You have to pick the retarded solution, though, and not the advanced one to obey causality. So if I give you an arbitrary distribution of matter, then from that you can calculate what the T mu nu is, and in particular you can calculate the S mu nu by this procedure. And from that you can get the distribution for the gravitational field, right? So there's going to be perhaps, right, some region of space-time where T mu nu of x is different from 0, right? And of course, in that region, also S mu nu of x is different from 0, right? And that needs to be fed into that integral, and then you do the integral, and out comes the gravitational field that you can measure at some distance from it, right? Now, of course, nobody said that this gravitational field has to be time independent, nor does the energy momentum distribution have to be time independent. And so as a result, of course, these fields in general will have a time dependence. And the simplest case, right, to analyze, of course, is one when there are no sources. So if you are in a vacuum, right, so in a vacuum, then T mu nu of x is 0, right? So it means we're just looking at some region where the T mu nu vanishes. So that could be somewhere out here, right? So in a vacuum, we just have box H mu nu is equal to 0, right? That, of course, is the wave equation. Is the wave equation. Well, of course, it's not the most general wave equation, right? Because we have encountered, for example, in quantum mechanics class, we have encountered the Klein-Gordon equation, right? Which is also a wave equation. So the wave equation we are talking here is a wave equation where the mass is equal to 0, right? So we find in the weak field limit that Einstein's field equations, just in the simplest possible case, which is in the absence of sources in empty space, to leading order in the gravitational field fluctuation, reduce just to the wave equation as for electromagnetism, if you wish, but with a mass which is equal to 0. So that means that gravity is described by some sort of massless particle, which is referred to as the graviton, right, which is the analog of the photon in electromagnetism. Right, so this, if you want, is the wave equation for the graviton. Right? The wave equation for the graviton is given by box H mu nu is equal to 0, and so that's the analog of the Klein-Gordon equation for a particle, a scalar particle that has a finite mass, except that here the mass is 0. Right? And of course, we know that this is not the end of the story, right? Because this is just what you get from lowest order in the weak field expansion. Right? So there's infinitely many terms that we have dropped because we looked at the limit when the fields are weak. And that is, of course, radically different from electromagnetism, right? Because in electromagnetism, that is basically the end of the story, right? In electromagnetism, when you're looking at electromagnetic fields away from sources, then the equation box A is all there is to it. Right? And you can solve that in terms of plane waves, and you have the full answer. Right? And that, in the quantum mechanical language, is the statement, of course, that the photon does not interact with itself, if you wish. Right? It's a linear theory, and if you have a free photon, then it just propagates to this room, following a wave equation which is of that type, for which the right solution is just a plane wave or a wave packet of some sort. Here, that is not the case. That is not the case, right? Because this is just the leading term in an infinite expansion, because the graviton satisfies this wave equation to lowest order in the field deformation. But of course, there's infinitely many terms, so it will interact with itself, and there's all sorts of nonlinearities which are just kind of go away when the field is weak, right? So nevertheless, we can see that things work out in a way that is very similar to what we have in electromagnetism, right? And we just have to then look at the next corrections and see, you know, how is it that then certain differences come about. In that respect, electromagnetism is very unusual, right? One is very lucky in the case of electromagnetism, because the photon just couples to charges, but the photon itself does not have a charge, so it doesn't couple to itself. So it is a theory that, from this perspective, is very simple, right? It's very simple. And this theory here that we have is not as simple because the graviton does couple to itself, and there's all sorts of difficulties that one encounters in dealing with that. And as a result, of course, this theory is also very rich, right? It has all these wonderful features that electromagnetism cannot exhibit because it is a linear theory, right? And so again, we see that the general theory of relativity is not going to be the easiest theory to deal with, right? Already at the classical level because of this nonlinearity, but the nonlinearity is nevertheless intrinsic. And so what we see here is that the particle has zero mass, right? That should not surprise us because we do understand, right, from a quantum mechanical point of view that if you want to have long-range forces, the particle has to have zero mass, because if it doesn't have zero mass, then you end up with a Yukawa-type potential, and you have a finite range, right? So the finite range is not going to go well with the things that we know about gravity. We expect gravity to have an infinite range. We expect interactions to fall off like 1/r, and so here we see another reflection of that fact that we do have indeed a massless particle, which is a good candidate for having long-range forces, right? And so if we had discovered that there was a mass here, then there would have been a problem, and we would have run into some sort of inconsistency, but that is not the case. So at this stage, what you're going to do is you're going to proceed a little bit further along the line of doing this comparison with electromagnetism, right? Because it clearly showed so far, right, that there is some analogy, that you can draw arrows between the two theories in comparing what is happening in one and the other as far as the field equations, as far as the invariance is concerned, and so forth. So we're going to pursue that a little bit more. And so that means we're going to do the same exercise that you do when you look at, in Jackson, at time-dependent fields. That is, you look at plane waves. So we're going to do that here as well. So we look at plane wave solutions, right? Again, a standard exercise also that we do when we deal with wave equations in quantum mechanics. And so here we summarize, right, all we have at this point. We have box h mu nu is equal to the source term, right? But we're going to set the source term equal to 0. We just want to analyze this plane wave by itself. So we have box h mu nu is equal to 0. And the other thing which you cannot drop, which we have to kind of take along with us, is the fact that this simple result was achieved by imposing this harmonic gauge condition, right? So there's going to be also the condition that d by dx mu, d by dx mu of h mu nu, right, is equal minus a half. We can bring it over this side. Minus a half times d by dx nu of h lambda lambda is equal to 0. I need to write in this form. So we have both of those equations to deal with. And so the next step is to write it as a plane wave. So we take h mu nu of x, and we write it as e to the ikx and e to the minus ikx. So here is our first plane wave, e to the ikx, right? Now, a solution to the wave equation is also e to the minus ikx, right? So we're also going to have e to the minus ikx. By the way, this is, of course, the Lorentz dot product, right? And, well, there's going to be some coefficient here in front, and that coefficient in electromagnetism, of course, it is just some e mu, right, times e to the ik dot x in electromagnetism for the electromagnetic field, because the field carries those Lorentz indices. Here we have to have something that has more indices, and so we're going to call it e mu nu, right? And we're going to have e mu nu over on that side as well, except that in general, these polarization vectors are going to be complex. So the second one will have an e star mu nu, right? And so k dot x is equal to k lambda x lambda, right? And so it's a superposition of plane waves, and of course the original field is real, which means that we're going to write a plane wave plus everything gets complex conjugated so that we make sure that this thing is actually real. And so that's our plane wave solution. So now we take this expression, right, and this is something that we have done many times by now, both in electromagnetism and also in the quantum mechanics class. You've seen this endless numbers of times, that you take this and you plug it in here, and of course you take derivatives, and the derivative act on the x, and so that brings down the k, and so you just get that k squared is equal to 0. So box h mu nu is equal to 0 just gives us that k squared is equal to 0. So that, of course, we knew already, because normally for a particle that has a finite mass, the k squared is equal to the mass squared of the particle minus the mass squared, depending on what conventions you use. But here the mass is 0, right? So this corresponds to a particle that has a mass equal to 0, right? Again, we knew that by just by looking at the form of the wave equation, which involves the D'Alembertian only. Right? But we also have the gauge condition, right? So we have the gauge condition as well. And so the harmonic gauge condition, so let me write it again over on this side. So we have that k mu is equal to 0. So that's from the wave equation, which is, if you want, is equation 1. And equation number 2 tells us something that is by the way, it is obvious that this polarization, so let me write this polarization vector. And it's actually a tensor in this case. So there's a polarization tensor that appears, which is independent of x, of course, right? It's just a number. And so the second condition tells us that the k mu times the e mu nu minus 1/2 k nu times e mu mu is equal to 0, right? So the polarization tensor has to satisfy this constraint as well, according to the harmonic gauge condition, right? What's next? Well, the next thing we want to do is show something that is very interesting, and namely that this particle has spin 2. This particle has spin 2, right? And not only that, but there's only 2 independent polarization states, right? And that is very interesting, and one has to really show it. I think it's something that we have to go through. There's a little bit of algebra, but it's absolutely key to the whole theory. So we have to do that. And so you'll have to bear with me as we go through this algebra. Keep in mind that how many components does the e mu nu have? Well, of course, 10, right, as you point out correctly, because the metric had 10 components, the deformation of the metric has 10 components, and the polarization vector at this stage has 10 components. So it looks like there's 10 different possible polarizations. Now, we know already in electromagnetism you start out with 4, but it comes down to 2 at the end, right? The 2 transverse polarizations for the photon. So here we want to find how many independent polarization states there are for a graviton. Right? And so that requires that we go through patiently through a little bit of algebra. It is algebra because at this stage there is no x dependence anymore. Right? The x dependence is gone because we're just dealing with plane waves. So these are all numbers. Right? So it's really completely straightforward algebra. Nevertheless, there's 10 of these e's. Right? So we have to be patient in keeping track of all of them. Right? Now, the thing that is going to play an important role is what is left over of general coordinate invariance, which is this gauge invariance, right? So we're going to write that out again, right? And so if you want, that might be equation number 3. And now the coordinate invariance has to do with, so remember that what is left over, so we wrote x prime mu is equal to x mu plus epsilon mu of x, right? That was general coordinate invariance. Right? And so that made the metric, or the h, transformed in a certain way. And there's 4 of these parameters, and they depend on x. So we need to bring those epsilon functions in, right? And the epsilon should not be confused with the e. Okay, the epsilon has to do with general coordinate invariance. Now, to bring it into this picture, we need to Fourier transform it so that we have an epsilon mu, which is just a number, right? So we're going to write epsilon mu of x also as a plane wave. We're going to write that also as a plane wave, which just like we did the other quantities here. And so we're going to write it as some amplitude, which is I epsilon mu. This amplitude, we're going to use the same name, right? But this one is now a number. It's now a number times a plane wave, namely times e to the ikx. Right? And so, and of course, there's a dot product here. Let me make sure that we see that, right? And so that's just like what we're doing there, plus the complex conjugate, right? Well, we have chosen to put an I in front here because it will simplify the equations in a little bit. Otherwise, we'll have to drag an I along all the time. So I'm going to put an I here. The second term has to be the complex conjugate of the first one because, again, this is real because it's a deformation in the coordinate. So it's going to be minus I epsilon mu star, right, e to the minus I k dot x, right? So it's another rewriting of a function in terms of its expression in k-space, right? So now we can calculate derivatives of this. Right? We can calculate derivatives, and the derivatives involve the k's and so forth. And so let me just write the answer for that. So now we look at the transformation law, which is h prime mu nu is equal to h mu nu plus d mu epsilon nu plus d nu epsilon mu, right? And we plug in Fourier transforms for everything, right? So Fourier transforms for everything gives us that, right, k-space, gives us that h prime mu nu of x is equal to some e prime mu nu, which is just a new polarization vector, right, times e to the I kx plus e prime star mu nu times e to the minus I k dot x with e prime mu nu. So how does that transform? Well, it transforms where the derivatives are replaced by ik, but because we had the coefficient here to be complex, there is no I, there's just a k. So e prime mu nu is equal to e mu nu plus k mu epsilon nu plus k nu epsilon mu. So that is what's left over of the gauge invariance. So this is left over gauge invariance. Right, so that's the third equation if you want, right? Because the first two were these. Okay. So again, to recap, we have rewritten for a simple plane wave, which is just the simplest setup we can have, just a simple single wave, not a wave packet, just a single wave. We have rewritten the wave equation, which just tells that k squared is 0. We have rewritten the harmonic gauge condition, which is the thing we have up there. And we have also rewritten the way the field transforms under these gauge transformations, which in momentum space or k space is just a simple term that has to be added to the polarization tensor E mu nu, right? And now it turns out, as I already mentioned some time ago, that the number of original degrees of freedom, well, was 10. And that is reduced because of these constraints to 10 minus 4, which is equal to 2. And that is what we want to show explicitly, right? We want to show explicitly that if we have to start with still 10 degrees of freedom, because that is our E mu nu, right? The E mu nu is the polarization We don't want to call it polarization vector because it is a tensor, right? But our polarization tensor has 10 components. And as a result of these various conditions, that brings it down to 4 and 4 again, and then leaves it just to 2, right? And so that is what we want to show explicitly. And to show that explicitly, the easiest thing, and I think I need at this point, well, I could write it over on this side, right? So we have number 3, if you want, which is that E prime mu nu is equal to E mu nu plus K mu epsilon nu plus K nu epsilon mu, right? So that would be number 3, right? So we want to work out what all that stuff means, obviously in the simplest possible setup, right? Because we are dealing with lots of amplitudes, right? And so to simplify the algebra, we're going to take the simplest possible plane wave, which is one that goes in the z direction, right? So we choose coordinate system to work out what happens. And so we're going to take K1 equal to K2 is equal to 0. K1 equal K2 is equal to 0. And then K3 and K0 is equal to some K, right, which is positive. Is equal to some. So this is a wave along z-axis, right? Or what we denote in this case is the 3-axis, right? Along the z-axis. And of course, k squared is 0, and that is satisfied by this choice, right? So we have a nice plane wave moving in this direction, right? Which is the 3 direction. And it has a k vector that is associated with that, which is in that direction. So we need to have a naught component as well, otherwise we run into trouble. So now we're going to write out, write the various conditions. So first of all, we're going to use the harmonic gauge condition. So that's the first thing we're going to write out in components with this choice of coordinate system, right? So that's this one, right? And that's easy to do because, of course, 2 of the components of k are 0, so you just have to look at the ones that survive for the k0 and the k3, right? And so we have E31. And by the way, the k appears everywhere, right? So the k, but the magnitude of the k is just k, so that's going to drop out from the equation because you have the k on both sides on whatever equation is not identically satisfied. So we get E31 plus E01 is equal to E32 plus E02 is equal to 0, right? So as I said, they're all proportional to k, and the k you just factor out. And that's one of them. Remember, we have different choices here because this index nu, right, can take on 4 values, 0, 1, 2, and 3. This is a free index. This one's summed over, but that one's free. So that's 2 of the equations, and there's 2 more. So we have E33 plus E03 is equal to minus E03 plus E00, minus E00 and this is also equal, again by another one of those equations, 1/2 times E11 plus E22 plus E33 minus E00. So that's all you get out of the harmonic gauge condition. Right? And so we're going to use those equations to eliminate some of the components. right? So use above to eliminate something. So let me do that over on this side. So I think you remember this because we're basically done with this one. We're done with the top, of course. So we basically just have to deal with this last one, which we can remember, right? So we are going to use the results of the harmonic gauge condition, and of course k squared equal to 0 as well, to eliminate some of the components. So we're going to eliminate E naught 1. All the E naught I we're going to eliminate, and E22 as well. Right? There's lots of, so there's an E naught 3, there is E naught 1, there is E naught 2, right? And there is an E22 here. So explicitly that means that E naught 1 is equal to minus E31, right? Well, that's of course from here. This is equal to 0, so we can write the E naught 1 in terms of E31, right? And similar equation, so E naught 2, same thing, right? You can read it out from over there, is minus E32. Right? And E naught 3 from the second equation is minus a half times E33 plus E naught naught. And finally, E22 is equal to minus E11. Okay? So those components are gone. Those components are gone. Naught 1, naught 3, naught 2, and 2 are gone. So now we need to focus on the remaining ones. And to focus on the remaining ones, right, so we can actually erase this as well. We're going to use now this gauge invariance property. Right? So next, so use this gauge invariance, which is E prime mu nu is equal to E mu nu. Right, plus, well, I can write out k mu epsilon nu plus k nu epsilon mu, right? Use this gauge invariance property to see how the remaining components transform. Right? Well, the remaining components are what is not listed here. So, for example, E11, right? E22 is gone, but E11 is still there. Right? So E11 prime is equal to E11. So this one doesn't change under that. Right? Doesn't change. E prime 1, 2 also doesn't change. E prime 1, 3 is E13 plus K epsilon 1. So that changes. That changes. E prime 2, 3 is equal to E23. E23 plus K epsilon 2. So that changes too. Okay. And well, there's a few more of these components which are non-zero, right? Because some are 0, but these are the ones that survive. So E prime 3, 3, right? That transforms as E33. E33 plus 2K epsilon 3. And finally, E prime naught naught is equal to E naught naught minus 2K epsilon naught. So let's stay at this a little bit, right? So we have, remember, we started out with 10 E polarization vectors. We started out with 10. We eliminated 4, right? Which are the ones that were eliminated here by using the harmonic gauge condition. So we are down at 10 minus 4, which is 6, and this is what we have here. So we have the 6 remaining ones. Right? And on those 6 remaining ones, we do a transformation, and that transformation still has an effect, right? In spite of the fact that we impose the harmonic gauge condition, there is still some invariance that is left, And so some of these E's do transform in some way. And so as we stare at this, we come to the conclusion that in fact, what can we do? Well, of course, what we can do, we can choose now the epsilons in such a way, right? We now have the freedom to choose the epsilons or to choose coordinates or to choose a gauge function, right, in such a way that out of these 6, we can make 4 to be 0. Very good, right? So we are going to choose the epsilon 1 in such a way that it cancels out with the E13, right? So we can set this one to 0, right? We can set this one to 0 by choice of epsilon 1, right? We can set this one also to 0 by the choice of epsilon 2, right? Epsilon 2 is going to be 2 minus E23 divided by k. And we can do the same with this one. We can set that to 0 as well. Why can we do that? Well, of course, you can see that the epsilons that appear in those 4, they're all different. They're all different. There is an epsilon 1, an epsilon 2, an epsilon naught, and an epsilon 3. So we can adjust all 4 components of the epsilon so that all of these 4 are 0, right? So by choice of the epsilon mu, right? So by the choice of epsilon mu, which is this gauge parameter or gauge function originally, right? Here is just a number. We can choose that to make those things vanish. And at the same time, we recognize that 2 components are unchanged, right? So they're going to stay the same. They're not going to be affected by this choice. And so we come to the conclusion that there's only two independent polarization. Well, again, it's not a vector, but it's a tensor, right? Or should I say 2 independent polarization components. Only, right? 2 independent polarization components only. If we look at the plane waves, it is just entirely straightforward algebra that is the case. And which are those components? Well, they're right here. They're right here. Right? And of course, it has to do with the polarizations that are perpendicular, transverse to the direction of propagation, right? Because the wave was chosen to propagate in the z direction, in the 3 direction, right? And these polarizations are, of course, like in electromagnetism, they are in the 1-2 direction, right? And so those are the only ones that are left over. So now we can do the following additional exercise, right? And the additional exercise involves, again, the use of quantum mechanics. And that is to find what the spin is of this quantum mechanical particle that satisfies this wave equation, right? So spin of graviton. Right, spin of the graviton is that we do rotation, so do rotation about which axis? Well, of course, the axis of propagation, so they could rotate the polarization vectors or components among each other. So the rotation about the z or 3 axis, right? And once you choose the z-axis, the remaining spatial axes are just x and y, so it's just a rotation in a plane, right? It's just a rotation on a plane. So that means that that rotation is r11, which is cosine of theta. This has nothing to do with the curvature. It's just a rotation matrix. And r12 is equal to the sine of theta, right? And r01 is equal to minus sine theta. Sorry, r12, the naught is, of course, not there. r21 and r22 is equal to the cosine of theta again. And the 3 and naught components are unchanged. We do a rotation in 4-dimensional space, but it has a submatrix which depends on theta. And so if you want, you can draw this as our k, and we're doing a rotation about this axis. So the remaining components are just 1 or 0, right? So r33 is equal to r naught naught is equal to 1, and all other r's are 0. Right? So we take just a rotation about the z-axis. So why do we do such a rotation? Well, we do such a rotation because, remember, these polarization vectors, well, they're supposed to be tensors, so they're supposed to transform in a specific way, right? So E prime mu nu is supposed to transform like an object that has two indices, right? We're basically dealing with just special relativity in this case, right? And in fact, this is a Lorentz transformation, except it's a very simple one where you just have a spatial rotation. So E prime mu nu, because it has two indices, transforms it two matrices R. So it has a E mu, right? And it has a E nu. And then there is a E rho sigma here, and rho and sigma here. Like that. And so each one is those matrices there. So we got to multiply them out and figure out what this is, right? Well, you can imagine that you get coefficients which are sines and cosines, and it is easiest to set these polarization vectors as write them as linear combinations of things. Namely, to define E plus minus, to define that as like a circular polarization type of combination, that is as E11 plus or minus I, E12. Remember, both of those are non-zero and they don't transform at all under a gauge transformation. And so to write those in this way, and to define some other ones, because we do have some other components as well. So for example, F plus minus, to define that as E31 plus or minus I, E33. And if you do that, then instead of getting sines and cosines, you just get phases, which is simpler. And so you get E prime plus minus, right? So the effect of a gauge transformation is now to just give a phase. And that phase is e to the plus or minus 2I theta times E plus minus. And on the F plus minus prime, it's also a phase, but it is 2 to e to the plus or minus I times theta times F plus minus. And E prime 33 is equal to E33, and E prime naught naught is equal to E naught naught. So those two transform like scalars, right? So we do find that that these fields transform. The plus and minuses fields transform in a very simple way. And in general, we can introduce the notion of helicity. So if you have a field that has a given helicity, then under a rotation, it will transform as e to the I h theta times the original field. And so we have that in our case, the E plus minus have helicity equal to 2. The F plus minus have helicity equal to 1, and the other ones have helicity equal to 0, which means that this is a scalar. This is a vector, right? A genuine 4-vector, and this thing here is a tensor, right? Or is a tensor. Now, if we go back, though, at what kind of fields we had to start with, remember that the F plus minus was defined as E31 plus or minus I, sorry, it's actually minus plus, I32. Well, those were exactly the ones that we could pick to be 0, right? They were the ones that could be picked to be 0. So these amplitudes are 0. And these amplitudes are also zero. Both the spin 0 and the spin 1 amplitudes can be taken to be 0. So you might think initially that the original gravitational field, the h mu nu, contains spin 0, spin 1, and spin 2. But in fact, today's exercise shows that even though that is a possibility in principle, by the time you apply the harmonic gauge condition and the invariance under these gauge transformations that we wrote down, you can set the spin 0 and the spin 1 components to 0, which means that you're only left over with a single spin 2 or helicity 2 component, which is the one of the physical gravitons. So we're pretty much out of time. So the conclusion that we come today is that if you look at the weak field limit, you actually learn some very interesting things. You learn that the graviton satisfies a wave equation, that gravitational waves satisfy a certain wave equation that corresponds to a massless particle. Not only that, out of the 10 components of that field, only 2 are physical. And they correspond to transverse polarization vectors, right? And those polarization vectors are very much like the ones in electromagnetism, right? You only can have this transverse polarization when it propagates in the z direction, and that the particle that is associated with it is spin 2, and no other spin appears. It's purely spin 2, and it only has 2 helicity states, which means that the spin is either aligned with the momentum or the k vector, or it is anti-aligned, just like for the photon. There's only a right and a left circularly polarized photon and nothing else. And here we have the same thing. There's only 2 polarization states which are possible. And so next time we're going to draw what those polarization states look like so that we can make a comparison with electromagnetism. And any questions or comments?
Yeah, what's
yes.
the interpretation of the helicity? Well, I didn't get that. Helicity is a spin.
So the interpretation of the helicity is that it is the projection of the angular momentum along the direction of propagation, right? The photon has 2 helicity states. So as you can see that already there, that there is a helicity, right? And so the neutrino also has the same story, right? It's one of the things that we discussed in class.
It only has always opposite.
Yeah, so it can either, so if it's propagating this way, it can either spin this way or it spins that way, right? And those are the 2 helicity states.
Okay.
Now, and so the graviton has the same story. It either spins that way or it spins that way. So you only have 2 circularly polarized states which are allowed. And now, what is, of course, kind of surprising, we discussed this in the quantum mechanics class, is that if the photon has indeed spin 1, then you would expect that the z component, or the projection of the spin along some arbitrary direction, there would be three values, right? You could have z equal 1, -1, and 0. But that is not allowed for a particle that moves at the speed of light. So if the particle is massless, then you can show that actually the spin projections that are possible are only 2, which is either along or aligned or anti-aligned with the direction of propagation. And so that happens to be the case not only for the photon, but also for the graviton. So only 2 possibilities exist. And we have shown that explicitly, right? So in this case, you can see exactly where it is coming from. And there is no discussion about it, except, of course, it's in the weak field limit. But it's a derivation that you only have 2 degrees of freedom. And so, yes.
A helicity of 1 would mean what? It only
spins this way. Right? And the other helicity is that it spins that way, right? So it's exactly like the photon, right? It's exactly like the photon. But the difference is, of course, that the magnitude of the spin is different. The magnitude of the spin, in the case of a photon, is 1. Here it's 2. So it's a different particle. It does have spin 2. Right? It does not have spin 1. That's a profound difference, right? And so nevertheless, the polarization vector structure is similar. We will see, though, in the next lecture that the kind of polarization states that you have for a spin 2 particle, they correspond to shear waves, right? So there is a little bit of a difference on how this polarization works and acts. It is in the form of shear waves and not in terms of polarization vectors, which is what you have for electromagnetism. You just have a vector which, if the wave is going this way, is either polarized this way or that way, at least for linear polarizations, right? And so here it's a shear wave. And so that we need to discuss. We're going to talk about that next time. Yes. Any other question?
What about beyond the weak field limit? Are there any general results that?
beyond the weak field limit, things should not change, right? Because now, if we look at it from the experience of quantum mechanics, we have a wave equation, and first look at the propagation of the particle on its own, and then when you go beyond the weak field limit, what happens is the particle interacts with itself. That's not going to change the spin structure, is it? I mean, this particle has spin 2, and then it self-interacts. So from the point of view of quantum mechanics, we don't expect this result to be modified in a significant way, except, of course, that it will interact with itself. We're well familiar with particles that interact with each other. Of course, there's already some interaction in electrodynamics, but even more so in gauge theories, where all these gauge bosons interact with each other. That is not going to change the spin. That doesn't change the spin here either, right? Yeah.
But the graviton probably won't obey that simple wave equation.
The graviton, well, it self-interacts. So, of course, in the end, there's all sorts of nonlinear terms, right? But that's the nature of the animal. The nature of the animal is that a graviton, as it propagates to this room, carries energy and momentum, and therefore will interact with itself. So it's a nonlinear theory because of the fact that it couples to energy and not just to charge like the photon. So, yeah, we just have to live with that. And, of course, that makes the theory particularly fascinating, right? I mean, these nonlinearities, you can view them from different perspectives. On the one hand, you can perceive them as a big nuisance, right? Because it makes everything so much more complicated. At the same time, it just makes the theory so immensely richer, right? Because you have that the graviton interacts with itself, right? That it always, carries with it this package of energy and momentum that self-interacts. So it's fundamentally different from electromagnetism. All right, so then I'll see you next week.